Namaste and a very warm welcome to this course on mathematical foundations for machine learning. In the last couple of weeks, we looked at the idea of vector spaces, vectors, vector spaces, subspaces, bases and stuff. And in the last week, we looked at linear transformations and eigenvalues and eigenvectors. If you had seen in the last 2 weeks lectures, we were just playing around with the fundamental operations on the vector spaces, namely the vector addition and scalar multiplication. We were calling the individual elements of a vector space to be the what would you call vectors, and we from our early school knowledge we have been taught that vectors are something which have magnitude and direction, but when we spoke about vector spaces we never spoke anything about the notion of direction or magnitude. In fact, we were just taking vectors to be abstract objects or elements of vector spaces. For example, we could actually say that look, polynomial of degree less than or equal to n, collection of all polynomials of degree less than or equal to n defined over a real field is going to form a vector space. Therefore, every element in that vector space is actually a polynomial, for which we were not really in a position to say that this is the direction of this. We looked at the system of a set of let us say real symmetric matrices of dimension 2. That means we are looking at say 2 by 2 matrices, real matrices, symmetric matrices, and we said that this collection is going to be a vector space over R, and every element of this vector space, this set was basically a matrix. But nowhere we actually brought the idea of this magnitude or the direction. We were completely I mean we completely ignored those two ideas, but we are talking only about very fundamental elements of vector spaces being vectors. Now, in this week's lecture we are going to bring in this notion of the so called magnitude and the direction, and we are going to introduce this idea of magnitude and direction through the idea of inner product or the dot product operation that we are going to equip the vector space with. And we are also going to look at projections of vectors which form a very key component of machine learning, and we will also look at specific focus on real symmetric matrices. So, the focus of this week's lecture would be on orthogonality and projections and real symmetric matrices. That will be the focus of this week, and we are going to start with the idea of orthogonality by bringing in the notion of inner product or dot product of vectors in a vector space. With that, we embark on a journey in which we are going to look at a very beautiful set of concepts based on orthogonality and see how we are going to use that in our machine learning ideas. Okay, so let us get on with the idea of the dot product or inner product on a vector space. So, let us look at that. So, let us do this. Let V be a vector space over R. Let V be a vector space over R, and we know that with operations, let us say our vector addition and scalar multiplication. So, now what are we going to do is let us take a simple example. So, what I am going to do is I am just going to look at a very simple example where let me take let V be equal to R2. So, what am I going to do? I am going to look at the 2 dimensional space where in which the let us say I have this, let me take this to be let us say the u1 axis and this to be the u2 axis. Now, what I am going to do is okay, let me put this as x1 axis and x2 axis. So, I have x1 and x2 axis, and let me take a specific vector here which I am going to call as the u vector. So, I have this vector u whose components are say u1 u2. This is what we have. Our components of the vectors are basically the components say u1 u2, where u1 is the you know that is the x1 coordinate and u2 is the x2 coordinate that you have. So, basically we know that this is a vector, basically it is what do you say, it is basically some kind of a directed arrow from the origin to the point u1 comma u2. Now, what we do is we define the dot product, which also we call it as the inner product, dot product of two vectors, let us say dot product of let us say two vectors in R2. In R2, how are we going to define? We are going to say that say for example, I have this vector u which has components u1 and u2, and we have this vector v whose components are v1 and v2. This arrow indicates that it is a directed line from the origin to the point v1 v2 on the xy plane, and this is basically a directed arrow from origin to the point u1 comma u2. So, we are going to define the dot product. So, we define the dot product of two vectors say u and v in R2 as let us say u dot v is equal to u1 v1 plus u2 v2, right. So, we are going to define this as u1 v1 plus u2 v2. So, let me put this as let us say ui summation ui vi, I is equal to 1 to 2, right. This is also called as the inner product of the two vectors. We also call this as the inner product. So, if you basically inner product or the dot product of any two vectors in say Rn, we will generalize this result across Rn of any two vectors in Rn is defined as u dot v is equal to u1 v1 plus u2 v2 plus etcetera un vn. It is also easy to see that the dot product u dot v, which is basically given as sigma ui into vi, I is equal to 1 to n. It is nothing but I have let us say I have this vector u which is nothing but say u1 u2 etcetera un, and we have this vector v which is basically v1 v2 etcetera vn. Now, what we see here is when I say u dot v, it is a component wise multiplication and then addition of this product, and you can very clearly see that this is nothing but if I take u vector to be this column vector and v vector to be that column vector, then what we have is u dot v is nothing but u transpose v, which is also equal to v transpose u, which is nothing but v dot u, which is nothing but sigma ui vi, which is also equal to sigma vi ui. I is equal to 1 to n, I is equal to 1 to n, right. This is the dot product that we have, right. So, we define this dot product. So, by definition we say that u dot v by definition is sigma ui into vi, I is equal to 1 to n, right. This is the thing that we have. Now, let us take let us consider this. Suppose I want to look at the dot product of, suppose we want to look at let us say u dot u, the dot product of a vector with itself. Now, what happens there in that case? So, u dot u is nothing but I mean let us consider for example, where u is in R 2. Again we will generalize this notion to R n. So, where u is an element of R 2, that means u has 2 components. So, u dot u is nothing but we have u 1 u 2 dot product with u 1 u 2, which is nothing but u 1 squared plus u 2 squared. This is something which we already know. Where is that? If you take this vector, say this is at the point say u 1 u 2. So, basically this is u 1 and that is u 2. This is the vector u that we are looking at. So, what does it say? It says this distance is going to be u 1 and that distance is going to be u 2. So, what do we have? We have the length of, so u dot u basically tells that it is the squared length of the hypotenuse. By Pythagoras theorem we see that this is the squared length of the hypotenuse, which is u 1 squared plus u 2 square, which is basically our Pythagoras theorem. Pythagoras theorem, right. We have u dot u is u 1 square plus u 2 squared. So, basically what we have is when you take a dot product of the vector with itself, we end up getting the squared length of the vector, squared length of the vector. Of u. Now, you take the square root of this, you basically get the magnitude of the magnitude of the vector u. Remember, we were actually saying that we never bothered about the idea of magnitude or direction till the time we were just playing around with vector spaces and the idea of vector addition, scalar multiplication. Now, with the introduction of this dot product or the inner product idea, we are able to get the notion of the magnitude of the vector, which is basically the dot product of a vector with itself, that is the squared length of the vector. So, we denote this as basically, this is called the squared magnitude, u squared it is called, where this notation is called the norm of u, norm of the vector u, right. So, that is what we have. So, let us look at some important properties of this dot product or the inner product. So, some interesting properties. We will say properties, every property is interesting. So, we will say some properties. The first one that we see is u dot u, which is basically sigma u I squared, I is equal to let us say 1 to n. If you look at this u I squared, this is basically sum of squares that we have, u 1 square plus u 2 square plus u n square. This is sum of squares that we have, and sum of squares is always greater than or equal to 0, right. It is always greater than or equal to 0. So, what we are going to do is we are going to say this is greater than or equal to 0 for let us say every u in R n, right. For every u in R n we have u dot u is sum of component squared, and what is interesting is sum of squares can be 0 only when each of the component is 0, right. Otherwise, it has to be a positive quantity, it is always a positive quantity, and it will be equal to 0 only when all the components of the u vector is going to be 0. So, what are we going to say? So, we are going to say that is equal to 0 only if u is the 0 vector. If u is not the 0 vector, then the length of the vector u dot u, the length of the vector is always a positive quantity. This is one thing we must remember. The second property that we have is we want to look at u dot v. U dot v is nothing but sigma ui into vi, I is equal to 1 to n. Again I am looking at u and v in Rn. So, we have ui dot ui into vi, sum of products, component wise products we are going to do, and we know that the product of two real numbers a into b is the same as the product b into a. So, I would do this reverse. So, I would say this is nothing but vi into ui, I is equal to 1 to n, which is same as v dot u, right. That means the inner product operation basically is commutative. You take u dot v or v dot u, both will be the same. So, in fact we have a notation for this dot product or inner product. We are also going to put it this way, u dot u within angle brackets. So, this is also a notation for inner product, okay. And we are going to say that this is equal to u dot v is nothing but v transpose u, which is also u transpose v, which is nothing but v dot u. This is more important. So, the dot product is basically obtained by taking transpose of one vector and then multiplying it with the and then doing a matrix product with that other vector, let us say u. So, you have a vector u and v which are of the same dimension, that means they are from the same vector space. Now, what we have is we define u dot v to be v transpose u or u transpose v, that means you have u1 v1 plus u2 v2 plus etcetera u and vn, which enforces the condition that both of them must have the same number of components. So, that is what we have, right, for all u and v in Rn. That means both are n component vectors. So, this is one thing which we need to understand. What is the third property that we have? Suppose I want to look at this. Let us say I want to look at the dot product of u with, let us say, v plus w. That means v is a vector, w is a vector. So, I want to look at the dot product of u with v plus w, that means the resultant of these guys. Let us see what happens here. This is nothing but u dot v plus w, and by the very definition of vector space we know how to add two vectors. U v plus w is going to be the vector addition. So, we know how to have these two. So, we are going to have u dot, I am going to have this v plus w as a vector which is going to be represented this way. So, let us take this. So, assume that okay, for we will do this for u v w in Rn, that means all of them are n component vectors. Now, v plus w is basically the following: v plus w is v1 plus w1, v2 plus w2, etcetera vn plus wn, right, vn plus wn, this is what we have. And the u vector is already known, this is basically u1, u2, etcetera un. So, how do we find the dot product? This dot product u dot v plus w is pretty simple. It is like this: u1 into v1 plus w1 plus u2 into v2 plus w2 plus etcetera plus un into vn plus wn. Now, we know that the distributive property, we know that. So, I am going to take this as you are going to have product of this basically multiplication distributes over addition. So, I am going to write this as u1 v1 plus u1 w1 plus u2 v2 plus u2 w2 etcetera plus un vn plus un wn, which is basically saying, look, I have this, what is that? I have u1 v1 plus u2 v2 plus etcetera plus un vn plus u1 w1 plus u2 w2 plus etcetera plus un wn, which essentially says this is nothing but u dot v plus u dot w. Therefore, what we are going to say is the dot product or the inner product of u with v plus w is basically this is equal to the sum of inner products, that means u comma v, the inner product of u v plus the inner product of u w. So, this is something interesting that we know. And the last one we want to look at this one. So, this is property number 4. Let C be some scalar, real scalar, now what I want to do is, and let me take u and v to be u comma v be elements of R, that means both of them are n component vectors. Now I want to look at the dot product of a vector with a scalar multiple of another fellow and then see what happens. So I want to look at the dot product of C times u with v. What is that? C times u with v is nothing but C u1 v1 plus C u2 v2 plus etc plus C un vn. This is what we have, right, which is the same as u1 into Cv1 plus u2 into Cv2 plus etc plus un into Cvn, which is the same as the following. What is that? C into u1 v1 plus C into u2 v2 plus etc plus C into un vn. Now what does this mean? This is interesting. Now if you look at this expression, if you look at this, the one that we have written here, right, if you look at this, it says first of all we took the scalar multiple of the vector u and then did a dot product with v. This is equivalent to saying u dot scalar multiple of v, which is also the same as scalar multiple of u dot v. This is what we have. So what we are going to say is, we are going to say the following, we are going to say that look, this implies the dot product of C u with v, that means scalar multiple of u with v is nothing but, let us do this, is nothing but the dot product of u with the C scalar multiple of v, which is nothing but the scalar multiple of the dot product u comma v, right. This is pretty interesting. So you take the dot product of a scalar multiple of vector with another vector v, it is the same as taking the dot product of u and v and then multiplying with the scalar. So these are basically pretty interesting. So in fact if we look at it very interesting, this v u comma v plus w is basically talking about vector addition, which is one of the most important properties that we have illustrated in the vector space, the operations that do on the vector space. And this one talks about scalar multiplication, which is yet another interesting operation that we talk on the vector space, right. So this is what we have. So what we are going to do, we are going to make one important comment here. So recall from the idea, from the notion of our u dot u, so we just want to make that. So we saw that u dot u is nothing but the inner product of u with itself, which was basically the squared norm, the squared length of u, this is what we had. Therefore, the length of this vector u is nothing but square root of u dot u. This is important, right. This is something which we want to look at. Okay. Now why do we need this? So what is so interesting about knowing all these things, the dot product, the dot product and then magnitude and so on. In fact if you look at this, let us say we can actually put this u comma v plus w, I can actually take this in terms of a scalar multiple. So let us do that also. So let us generalize this, we want to look at let us say the dot product of look at the dot product of a vector let us say u dot alpha v plus beta w. I want to look at the dot product of the vector u with alpha v plus beta w, where alpha and beta are scalars and u v w are, let us say, elements of R n, that means they are n component vectors. Now, what we have here, we have u dot alpha v plus beta w. We already saw that the dot product is going to distribute over the vector addition. We saw that u dot v plus w is u dot v plus u dot w. So, we are going to extend that property here. So, we are going to say that u dot alpha v plus beta w is nothing but u dot alpha v plus u dot beta w, and we already know that the scalar multiple the dot product of a vector with scalar multiple of another one is going to be the scalar multiple of the dot product. So, I am going to write this as alpha times u dot v plus beta times u dot w, and this property is what we call as linearity property of the dot product, linearity property. Then we also have the next important stuff which we saw, which is basically the commutativity. We said that the dot product of u with v is equal to the dot product of v with v with u. We call this as the symmetry property. We call this as the symmetric property. So, let me write this notation wise u comma alpha v plus beta w with this notation saying it is inner product. And the third one that we have, which was basically this, which said for any, let us say, u in R n, we can actually take it to be any vector space. We said that u dot u is greater than or equal to 0 and u dot u is equal to 0. Okay, let me put this, I think. Okay, we said that u dot u is greater than or equal to 0 and u dot u is equal to 0 only if and only if u is the 0 vector. This is what we had. We will see that this idea of the dot product of u with itself being greater than or equal to 0, this has a name. This is called as the positive definite property. We will revisit this idea of positive definiteness and positive semi definiteness when we do the real symmetric matrices. So, what we will take this property to be positive definite property. Okay. This is basically called the positive definite property. Now, remember when we studied vector spaces, we did something interesting. As I said before, for a vector space we were always bothered about the closure under vector addition and closure under scalar multiplication and the existence of the 0 vector. These were the fundamental operations that were there, basically the vector addition and scalar multiplication were the fundamental operations that were there. Now, what I am going to do is I am going to equip that vector space with yet another operation called the inner product. That means, I have a vector space V which is defined over a field, let us say F, with additions, vector addition and scalar multiplication operations. In addition to that, I am going to define a new operation called the inner product. I am going to equip this V. The vector space only had vector addition and scalar multiplication, nothing else. Now, what we are going to do is we are going to equip this vector space with another operation called the dot product, and the moment you attach this dot product property to the vector space, you will see that the vector space is closed under this inner product, then you will see that you have all the properties of the vector space being preserved with the what would you call you will see that it is closed under scalar multiplication and stuff. Therefore, that vector space which is equipped with the inner product operation, there is a name for it. We are going to call that as the inner product vector space, right. So, we are going to do that. So, what are we going to do? We are going to say the following. Let us take so let us do this. So, we define, let us take a definition now. So, what does the inner product basically do? That is something which we need to understand. You see, we took in this case we took the inner product, dot product, whatever it is, we did something. We said that look, we are going to define our idea of inner product here as this product wise or the component wise product plus addition. That means, I am going to take two n component vectors here, I am going to do the component wise multiplication and then add the product. In turn, what am I going to get? I am just going to get a sum of real numbers which is going to be a real number. Therefore, we are going to say that this inner product basically definition we are going to give. So, the inner product or the dot product, the inner product or the dot product of two vectors in a vector space V is basically a rule which is going to assign for any two vectors that you take in V, it is going to assign a real number. This is clear. So, what we are going to say in a vector space P or the V is, let us say some kind of an assignment is okay, is basically an assignment assignment for the two vectors let's do it. Let's okay, the inner product or the dot product in a vector space, we will put it this way. The inner product or the dot product in a vector space V over the field R, right, is a mapping, is a map that for any two vectors, let us say u comma v, in this vector space V, there is a real number which is defined as u comma v, the inner product u comma v, that satisfies the following properties. What are the properties? We have already seen. The first property is, let us say u comma let us say u comma alpha v plus beta w is nothing but alpha times the inner product of u v plus beta times the inner product of u w, and then b we have u comma v is the dot product of u comma v is the same as the dot product of v b comma u, and we have this for any u in V, the vector space V, u dot u is greater than or equal to 0 and is equal to 0 if and only if u is the 0 vector. That means it contains all the components to be 0. So, this is one important property that this is what we call as the inner product. Now, what we are going to do is we are going to extend this, we are going to say this any vector space. So, the vector space V with inner product defined on is called as an inner product vector space. Okay. This is called as an inner product vector space. Now, why do we want to study this idea of inner product vector space? We are going to make one important definition from here which will help us go further in this particular module. We are going to say if u and v are elements of V, a vector space, and inner product vector space, that means the dot product is basically defined there, and inner product vector space such that u dot v is equal to 0. That means the dot product of u with v is 0, that means u 1 v 1 plus u 2 v 2 plus u n v n is equal to 0. Here you see u1 is u is an n component vector, v is an n component vector, but what we say is the dot product of this, that means the component wise product, their sum, the sum of the component wise product is going to become 0, which is quite possible. In that case what we say is then we say that u and v are orthogonal to each other. U and v are orthogonal to each other. That means we are even talking about orientation of vectors with respect to each other based on the definition of the inner product. Only when the dot product is defined, I mean I'll be using inner product and dot product alternately. We see that only upon the definition of the dot product of two vectors we can even talk about the orientation of the two vectors, and we say that if the dot product is 0, then we are going to say that the two vectors are orthogonal to each other, right. That is pretty that is an interesting thing that we have. Okay. Now, so first of all we want to figure out what is the dot product. How did we even come to this conclusion that if u dot v is equal to 0, u and v are orthogonal to each other? What do we even mean by that? So, how did we suddenly put this u dot v is equal to 0 and then we say that u and v are orthogonal? That means there should be some kind of an angle coming into picture in the expression for u and v, I mean u dot v, which we have not seen yet. So, what we will do is we will stop here. In the next lecture what we will do is we will look at how did we even come to this conclusion that u dot v, if it is 0, we say that the vectors are orthogonal to each other. That means some angle term must come into this u dot v, which we really we have not seen explicitly, right. So what we will do is we will look at that in the next class, and then we will go on to define what is called as an orthogonal complement vector space, what happens with the orthogonal complement vector space, and from there we will go ahead with the idea of projections, orthogonal projections, and we will go further talking about isometry and stuff. So we will look at orthogonal transformations, and we look at something interesting out there, then we look at projections, and from there we go on to real symmetric matrix. So in the next lecture that we are going to look at, we are going to answer this question: how did we hit upon saying u dot v is equal to 0 implies u and v are orthogonal? That is something we want to look at, and from there we will proceed with the idea of orthogonal complement subspaces and so on. Thank you.